So we looked at fields of this form last time, where f is a field to begin with. You look at one variable polynomial rings with coefficients in this field, and if you quotient out by the ideal generated by a reducible polynomial, then what you get, this quotient ring, happens to be a field again. And I said these are the kind of fields that we want to look at. So we need a way to conveniently work with the elements of this field. See, the elements of this field are these cosets. So we actually played with this a little bit when we talked about examples of quotient construction. So I've pulled out that slide here. I just want to remind you of this part because this will be crucial. We need to be very comfortable with working with this thing. So here is what I had said then. You take a polynomial of degree n, little fx, in Rx. I took real coefficients, but now you can see everything goes through if I change real numbers by some arbitrary field. So f is going to be a field. So you take a polynomial of degree n, and then I'm not necessarily even irreducible. For this part, I don't need that. But let's just take n greater than or equal to 1. The claim is that the elements of this quotient ring, fx mod ideal generated by AF, are in one-to-one correspondence with polynomials of degree at most n minus 1, where n is the degree of the thing that you're quotienting by. And there's a more precise statement I can make. Let me make some space here. The more precise statement is that, so let's make this a lemma. This is going to be crucial. This is the lemma that I want to prove. More precisely, let be this denote the set of polynomial in fx of degree less than n. So degree up to n minus 1. Then define from this subset of fx to this quotient. I define a map defined by, call it alpha or something. Alpha of a polynomial, cannot call it f. F is the fixed polynomial. Alpha of g is g plus the ideal. So g going to the coset of g is an isomorphism. Isomorphism of vector spaces. It's not isomorphism of rings. The left-hand side is not a ring. Or at least it's a bijection. If you are not comfortable with isomorphism of vector spaces, it's just a bijection. So every element in this quotient ring can be uniquely expressed in this form for some polynomial of degree less than n. And we went through the proof essentially already. You give me, so I'll actually say this again maybe. Let's call this quotient S. You give me some G take a g in fx, or let's put it this way: take an element of the quotient ring. Then k looks like this for some g. The point is that this g need not have degree less than n to begin with, but I want to write k in the form that k equal to the coset of something where that something is degree less than n. What you do is you take this g and divide by f. So write g as fx qx plus rx, where q, r are polynomials such that degree of r is less than degree of f. You can do that by division with remainder. And now notice that this difference is a multiple of f, so g and r live in the same coset. So this element k is also represented by this r, and r indeed has degree less than n. And this shows that this map alpha is onto. Okay. So indeed, every element in this quotient ring can be expressed as coset of a polynomial of degree less than n. On the other hand, suppose, let's show that it's injective. Suppose r plus f is r1 plus f for some r and r1 polynomial of degree less than n. What does that mean? This means the difference of these polynomials is in the ideal generated by f. That is, f divides this polynomial. But then this has degree n. Whereas this guy, both r and r1 have degree strictly less than n, so this also has degree strictly less than n. Now a degree n thing can only divide something of strictly lower degree if that something else is actually 0. Because otherwise, any multiple of a non-zero thing will have strictly bigger degree, right? Any non-zero multiple. So this implies that this difference is 0. So r is r1. So if two low-degree polynomials represent the same coset, then those polynomials are the same. Okay. So that sort of proves the lemma. We rewrote this already. So we don't need this. Let me do one example of this to make this concrete. So change color. Let's take f equals q. So I look at qx, and let's look at this polynomial x squared minus 2. So we look at qx mod this polynomial. That's my quotient ring, what I'm calling S here. Let's call it K or something. By the way, this is going to be a field because this is irreducible. You can check in any number of ways that this is irreducible in Qx. So this is actually a field. What are the elements of this field? They look like what you're quotienting by is a polynomial of degree 2. So the elements here are all represented by polynomials of degree at most 1. So they look like this. In fact, it's isomorphic to Q cross Q as a vector space. And I emphasize that this is not isomorphic as a ring. Q2 also has a ring structure. The multiplication in this K is very different. It's not component-wise multiplication. But as a rational vector space, they are the same. And the isomorphism is given by taking A comma B to the corresponding coset. This is an isomorphism. That's what this lemma says if you unpack it in this case. That different polynomials of degree 1 represent different cosets. Okay? So now that you know this, I want you to notice something. See, something is wrong. Let alpha be the image of x in this K. So this is an element of K. And further, we already saw that Q can be identified in K via taking a rational number to the corresponding coset. And more, you see it again here basically, that up to degree 1 there is no identification. So you can identify the rational numbers as the corresponding cosets, and that would be an injective map. We saw that last time as well. Even pairs of numbers you can identify like this, and that would be an injective map. So if you do that, if you think of rational numbers sitting in K like this, so in particular 0 will be identified with the coset of 0, 1 will be identified with the coset of 1, etc. And alpha is the name for the coset of x. Then what is alpha square? Is x square plus the coset of x square. But that's same as so alpha square minus 2 is x square minus 2. The coset of that. But x square minus 2 is my polynomial, isn't it? So this is in the ideal, which means this is just the same as the ideal. Which means alpha square minus 2 is the 0 of this field. Which means alpha square is 2 in this field. That is after you have identified the rational number 2 with the coset of 2 in K, by the way. And this is the key. So so after you do that, really K becomes just A plus B alpha, all such expressions. And this alpha is really a square root of 2 in K. So you get K, so we say that K is obtained by adding a square root of 2 to the rational numbers. So you couldn't solve this equation in Q, but you wanted to. So what you did was you went to the polynomial ring and imposed the condition that this polynomial is 0, went to the quotient ring. And now this gives you a field. It's not much bigger. It's really as big as two-dimensional vector space over rational numbers. But in this field now, this equation has a solution. So this gives you a purely algebraic way to introduce numbers like square root of 2. And this alpha is not really the real number square root of 2, even though you can identify it inside real number. But I never had to introduce such a big creature as real numbers. So this is how extension fields are relevant in solving polynomial equations. Indeed, you can verify that this thing is isomorphic to Q adjoint square root of 2, where by square root of 2 here, I mean the real number square root of 2. So this is a subfield of real numbers. Okay. So this should serve as a motivating example for what we are going to study.